The next really important concept in quantum mechanics is this concept of an operator. An operator is an operation that we do on a function. In quantum mechanics, it turns out that for every observable property, like the position, the momentum, the energy, there's an operator that when you apply it to the wave function, gives the value of that observable, gives you the value of the position, the momentum, the energy for the state of the particle that's described by the wave function that you operated on. So these operators have a few things that are important. So the operators are always linear and Hermitian, and we'll talk about what that means. Let's be a little bit more specific though. So when we designate an operator, we put a hat over the symbol to mean the operator for x. And the operator for x is just multiply the wave function by x. So if I operate the x operator on the wave function, then what I'm doing is I'm multiplying the wave function by x. And so that's what the operation looks like. This is the operator. This signifies the result of that operation on psi. The momentum operator is minus I h bar, take the first derivative. So if I'm doing the momentum in the x direction, take the first derivative with respect to x. If I'm doing the momentum in the y direction, I'm just going to do the same thing, but take the first derivative with respect to y. And if I'm doing the momentum in the z direction, I want the same thing, but I take the first derivative with respect to z. So in this case, the operation has to do with taking the derivative of the function. And so if I operate the momentum operator on psi, what that looks like is minus I h bar, take the derivative of psi with respect to x. So that's the operation. And this is the operator. So for an operator to be linear, so when we talk about a linear operator, what we mean is that if I take some operator b hat and I operate it on a function phi plus maybe function psi times a constant c, that what I will get is the same thing as if I just distributed that operation through my functions. For an operator to be Hermitian, it's a little bit more complicated. So for a Hermitian operator, the operator is Hermitian if I'm going to integrate over all space. So we'll use tau to mean all of the possible variables for psi times the operator operating on psi star over all space. That has to be equal to the psi star times the operator operating on psi itself over all space. So if it's Hermitian, this will be true. The reason that this is important is because if this is true, so for any Hermitian operator, what we find is that psi star times the operator times psi integrated over all space is a real number. And what we're going to do is we're going to find that we associate this with the average value of the observable represented by the operator b hat. So if we want to associate this with an average value of an observable, then it had better be a real number. It can't be imaginary and it can't be some function. It has to be a real number. And so the operators have to be Hermitian in order for that to be true. And that's why all of our operators that are associated with observables are Hermitian operators. If the operators are linear, then if I have two different functions, so I have a system that's a combination of two different waves, the observable for that system is the sum of the observables for the two different waves. And that is something that makes a lot of sense, because if our system consists of two different things, then that each have different energies, then the total energy of that system ought to be the sum of the energies of the two different things. And so this idea that energies are additive, that the momentums are additive, that occurs in classical mechanics is also true in quantum mechanics, and that's ensured by the fact that all of our operators are represented by linear operators. So there are a couple of other properties of operator math that we should know about. One is that if we have a bunch of operators operating on a function sequentially, that we need to read this, so we need to think of order of operations. So the way that we need to read this is that we first need to operate C on psi. So we go from this out to from the right out to the left. So we do this first, and then we take that result and we operate B on that result. So that's the second thing we do. And then the third thing we do is we take that result and operate A on that result. So the order of operations always goes from right to left. And that's important when you're doing some operator math. Okay, the other thing that's important about operators is that they do not, in general, some do, but in general, they do not commute. In other words, if I operate B first and then A, it is not necessarily equal to the same thing as if I operate A first and then B. And we designate this idea by using what we call a commutator. So a commutator is written as A hat, comma, B hat in square brackets. And that commutator is equal to A hat, B hat, minus B hat, A hat. So notice that if this commutator is equal to 0, then the result of operating A first and then B, or B first and then A, is going to be the same thing. And so we say that the operators commute. So only when that commutator equals 0 do the operators commute. And we'll see a little bit later why this is important. It turns out that it is related to the uncertainty principle. So it's probably useful to collect all the operators that we'll be using this semester together in one place so that you have an easy place to find them. The momentum, the linear momentum, depends on what direction we're looking at, and it's minus I h bar, take the derivative with respect to that direction. For position, we just multiply by the position, x, y, or z. For the kinetic energy is momentum squared divided by 2 times the mass. And so we just take the momentum operator, square it, and divide by 2 times the mass to get our kinetic energy operator. So that would be in one dimension. If I'm in 3 dimensions, I have to take the partial derivative with respect to each of those directions and add them up. Second derivatives added up is something that we call del squared in physics. And so I can abbreviate this kinetic energy operator as minus h bar squared over 2m del squared. Remember that del squared operator is just taking these second derivatives and adding them up. Potential energy is just take the potential energy and multiply the wave function by the potential energy. And for angular momentum, we get this by crossing the position vector into the momentum, the linear momentum vector. And so we have an angular momentum in the x direction, y direction, and z direction. And then if we want the total angular momentum, the magnitude of that angular momentum, we can look at L squared, and that's just the x direction squared, the y direction squared, and the z direction squared, and then the total magnitude of that angular momentum would just be the square root of this.